I have a box dangling from a string. Simple enough. This box is going to be drawn upwards into the ceiling by a winch that's going to accelerate the box upwards at 1 meter per second. Sorry, 1 meter per second squared. So the box is being accelerated upwards at 1 meter per second squared. The box has a mass of 15 kilograms. I'd like to find out what tension will be required in the string in order to accelerate the box upwards. So I'm saying what the question is. I'd encourage you to write that down so you at least know what it was that we're started with. What tension in the string would be required to accelerate the box upwards at 1 meter per second squared? Again, we have a series of questions that we can ask, a set of steps. If you follow this set of steps, it should help guide you to the answer. It won't give you the answer. It'll guide you to an expression that could be used to find the answer. And those are different things. So let's start at the beginning. You need to decide before we even get going whether you believe this is going to be a first law problem or a second law problem. And the clues are there. It's very clear whether this is a first law problem or a second law problem. Is the acceleration 0 or not? No. This object is accelerating, making this a second law problem. So right away, I want to start this by saying the net force on this system is equal to ma. This is a second law problem. Starting with that in mind. My next step is to draw a free body diagram. Now, I've tried to say this, and I don't know why I'm wasting my breath, but I'm going to say it again. We use the free body diagram in here. We use it to solve our problem. This one's not complicated, but future ones will be more complicated. However, you'll be asked to draw a free body diagram on your test. A free body diagram is just a dot with arrows on it, and the arrows must be ruled using a straight edge. You can have no other information on a free body diagram. So in your test, there'll be the free body diagram that you draw for me to grade, and then there's a free body diagram that you will draw in order for you to solve the problem. Do you understand the distinction? So there might even be 2 boxes on your test, one that says this is where the free body diagram by itself goes, and this is where you can do your work for the free body diagram to solve the problem. However, a free body diagram begins by reducing every object with mass to a single dot to remove the extension, meaning we don't care about the shape of the object. All we care about is that the object has a center of mass. We are saying that these forces act on the center of mass of the object. Next, we go down our list of forces and ask if each of these forces may or may not be acting on our object. We'll start with the fundamental forces. And I'll say something like in class, are there any fundamental forces acting on the object? Your answer is always going to be yes. This is pretty easy. Unless we're out in the middle of space somewhere, our objects are going to be experiencing gravity. So it's a pretty easy one to get right. If you want to get something right today, that's an easy one to get because you can get it right away before anybody else if you're fast. So is our object experiencing any fundamental forces? Yes. Which one? Gravity. That's right. So I'll draw a downwards arrow indicating the force of gravity. In drawing this arrow, one of the things I want to impress upon you is we know that this arrow is 150 newtons long, right? This is the weight of the object. It's mg. We talked a little bit about this yesterday. So it sets the scale for everything else. When you're deciding how long to make this arrow, recognize that this arrow helps you determine the length of the other arrows you're going to draw, because it's likely the one that will be given to you. Although every arrow is supposed to indicate a force, you have to give it a label, and there are acceptable labels and unacceptable labels. For example, you can't label this G. They won't accept that because there is a constant of nature that is capital G. On the other hand, like if you look in your textbook, they tend to like FW or FG or FG. Grab any textbook you want, and there's lots of different ways that these are labeled. However, I tend to label weight, and this is allowed, just capital W, because this is the weight of the object. And if you have 6 objects, then you can have weight 1, weight 2, weight 3, instead of F sub G sub 1, F sub G sub 2. You get what I'm saying? So I tend to use the first letter of the name of the force, and that's acceptable to College Board. You can also do just mg, that'll be fine. They'll accept both of these. But I'm gonna stick with just first letter of the forces. Now, once we've handled the fundamental forces, we now go to the contact forces, and each contact force that we talk about has a specific thing that lets you know whether it's there or not. So, sorry, I gotta sneeze. So you guys kind of have some instructions here that will help. For example, is there a string or a rope or a cable attached to the object?
Yes.
Yes. Now, drawing this arrow, you don't have to think very much on it. It has to be drawn in the direction of the cable or the rope or the string. So you only have one choice there, and that's to draw an upwards arrow. The only thing you should consider is whether that arrow should be the same size, smaller, or bigger than the weight. Well, I think there's information to help you make that decision. The system is unbalanced. The forces, therefore, should be unbalanced. And so it is likely, since it accelerates upwards, that the imbalance should be upwards. So I am intentionally trying to draw a force that is longer upwards than the weight is downwards. And you should be intentional as well. Are there any springs connected to the object? That throws out Hooke's law. Is the object associated or resting on a surface?
No.
So there's no normal force. Is it sliding along a surface? No frictional force. Unless you're really sure to use it, there's not going to be air resistance in your problems. They don't try to trick you there. They tell you if there's air resistance. Mostly because they'd have to give you an expression for air resistance to use in the problem. So are we going to use air resistance in this one? No, we're not going to. And we don't have the buoyant force in this class, so we have reached the limit of the forces. But, hear me out, there can be other forces in our problems. Just because it doesn't fit this list doesn't mean there won't be something that may be acting on the object. Sometimes you'll have to make up a name for a force. They might have a hand pushing on a book. You might just say, well, that seems like an applied force. I don't know what it is. And it's okay to make up a symbol. Generally, whatever symbol that you want will work unless they tell you to use a specific symbol. Now, we're done drawing all the forces. This is a free body diagram. If all you need to do is draw a free body diagram, you'd be done. But we use the free body diagram in here. So after putting in our contact forces, we're going to, part C, apply a coordinate system to be used to solve the problem. Our coordinate systems are going to be two-dimensional for the most part. This one's actually one-dimensional, but we will still draw in a standard Cartesian coordinate system, which means an X and a Y axis. In making a decision about how to do that, I'm giving you some guidance here. There's 2 priorities that you should be using in deciding how to draw this. But the truth is, you can draw this any way you want to. But there are ways to make your problems easier and ways to make them way harder. I'm telling you to prioritize drawing the positive direction in the direction of the acceleration. I'm saying use that as your priority. So we know the direction this accelerates. It accelerates upwards. So it would make absolutely no sense at all to draw a coordinate system that's like this direction, right? And make that the positive X direction. Because if you did, then the Y direction would be like this way. And that would mean our object is accelerating in both the X and the Y direction. Do we think that that's a good idea for us? No. The best way to do this is to follow the priorities and choose a coordinate system that is aligned with the direction of the acceleration. So I'm going to choose a coordinate system in which positive Y is located upwards and negative Y is located downwards. And although there's no lateral forces, I'm still going to draw in the X direction just to be consistent. I've drawn a coordinate system that could be used to solve this problem. Now, I'm going to move on to the next thing. Are there any off-axis forces that need to be broken up, bless you, into components? Are there any forces that don't lie completely along the X and Y direction? No, so I can leave that step out. Moving on, step 3, apply Newton's laws. Well, Newton's law is a set of instructions. We've already chosen which law we're going to use. We're now going to take that law and break it up because our math is only one-dimensional. So we have to have net force in the x direction and net force in the y direction. Moreover, one of these is ma and one of these is 0. We forced our problem to do that by making the acceleration line up with one of these directions. So which one is it? Which one is 0 and which one's ma? X is 0 because there's no acceleration in the x direction, and we forced the y direction to be the sole direction of the acceleration. That's right. Now remember, this is a set of instructions. Add up all the forces in the x direction and set them equal to 0. That's what this says. Add up all the forces in the x direction, set them equal to 0. Are there any forces in the x direction? No, so I can kind of leave that out. Add up all the forces in the y direction and set them equal to ma. That's my next step. So I'm going to look at my picture here. It looks like tension is in the positive direction, so I'll say positive tension. Weight is in the negative direction, so negative weight, and I'll set that equal to ma. That's it. That's what Newton's laws do. So Newton's laws will generate a relationship. That relationship may or may not solve your problem. But that's what Newton's laws tell you to do. Now, I know you're thinking this was so stupid easy. In fact, you've probably written nothing extra because this is so bonehead easy. Trust me. Maybe put some stuff in there about what step corresponds with what, please. Now, we were asked to find the tension. We were specifically asked, and we have it right there. In fact, we can solve that for tension. We can complete the question. Tension equals ma plus w. But that's not an answer. At least not one that's sufficient. We know more things. For example, we have a set of possible substitutions. We should consider those. They gave us the mass of the box for a reason. That probably has to do with the fact that that's telling us the inertia of the box, but it's also there to tell us the weight of the box. Weight is equal to mg, so I can make a substitution here. This is where you as reasonable scientists have to now start solving the problem, trying to find a way to answer the question. Newton's law generated an equation. Can that equation be used to solve the problem? Now that I have this, I probably can start plugging some numbers in. Most of the time, our answers will be expressions. But sometimes they'll give us numbers. This is a numerical one. We're going to do some numerical ones in the beginning. Mass is 15. Acceleration was 1. Plus mass, which is 15. G is 10. This must be what the tension equals. 15 times 10 is 150. 15 times 1 is 15. 150 and 15 is 165 newtons. And that's all she wrote. We're done. We have found an expression for the tension. Which it's important to me to note to you that it's greater than the weight of the object. Yep.
Why is G10?
Acceleration of gravity. We could use 9.8, but we're allowed to use 10, so we will. All right. Let's see if you guys can do it. I'm going to give you another one. I just want you to do the same thing. Maybe a little different to make sure you're paying attention. You are going to go for a ride in an elevator. So you are in the elevator. There's a cable that attaches to the elevator, and you are going to be accelerated downwards while the elevator is getting up to speed to return you to the first floor. And it will accelerate at 2 meters per second squared for a short time. let's say you have a mass of 75 kilograms. What is the force of the elevator on you while you are accelerating in the elevator? That's the question. What is the force of the elevator on you while you are accelerating downwards? I'll give you about 5 minutes. Is this a first law problem or a second law problem? So we're going to start by saying that the net force is equal to ma, for this is the second law problem. I believe the forces will be unbalanced. I'm going to begin by drawing a dot to represent my person. And I'm going to start asking myself what forces are acting on the person. Is the person experiencing any conservative forces or fundamental forces? Yes. Yeah, so I'm going to draw an arrow representing what force? Gravity. That'll be a downwards arrow that represents the weight of the person. Is the person in contact with any string, rope, or cable? I don't think so. I've been in a lot of elevators and I've never been in contact with a rope in any one of them. So I don't believe so. I think the rope or cable might act on the box I'm in, but not me directly. So I'm going to move on. Am I attached to a spring?
No.
No. Is there any surface that's attached to me or pressing on me?
Yes.
Yes. The floor is pushing on me. And by definition, a normal force must apply a force that is perpendicular to the surface in contact. So if I'm standing on the floor, it must be pushing up on me. So I'm going to draw an upwards arrow representing the normal force on me, and I will label it as a capital N. Am I sliding along a surface? No, so I don't believe there's a frictional force. Do I have to deal with air resistance or drag in this problem? No, the air is moving with me, and we don't have the buoyant force. I believe I've identified all the forces that are acting on my system. It's now time for me to apply a coordinate system to this problem. So in applying a coordinate system to this problem, I need to choose what direction to make the x or y. Since the system is accelerating, I think it makes the most sense to make my positive direction downwards. Try and align my coordinate system with the direction of my acceleration, positive y. I am accelerating downwards. You don't have to do it this way. I'm just telling you, if you do, you'll find it's easier. There's a couple of reasons for that. Next, I'll make upwards negative y. And I will draw in the x direction, but I don't really believe I need it. Are there any off-axis forces? No. So now I can begin applying Newton's law. I'll take Newton's law and break it up into the net force in the x direction and the net force in the y direction. Is the net force in the x direction 0 or ma? 0. Is the net force in the y direction 0 or ma? Ma. All right. I don't think I have to evaluate anything in the x direction, but in the y direction, I appear to have two forces. Positive weight minus normal force equals ma. I was interested in the normal force acting on the person. That is the force of the elevator pressing on the person. And the elevator presses upwards on me. So I'm going to solve that for n. Now let's see, that means normal force equals weight minus ma. I added normal force to both sides and subtracted ma from both sides. Any questions? That's what Newton's laws can provide you with. Now, there's probably more because I think I have more information. I know that the mass of the person is 75, and I can substitute in mg for weight. So that'll be the next thing I'm going to do. I'm going to see if I can get to a better solution. But Newton's laws end here. But there's more that we can do with this. So let's see, mg minus ma Mass was 75, g is 10, minus 75 times 2. Any questions? 750 minus 150 gives me 600. The floor presses upwards with 600 newtons of force. It's pretty straightforward. Now keep in mind, my body is 750 newtons of weight. The floor presses with less force than my weight. Gravity is actually what's bringing the elevator downwards. And in such case, me. I just have to apply less force than my weight and let gravity do the work. But be aware, I want to make sure that the normal force in the elevator is enough so that I don't feel uncomfortable. That's what they're trying to do. They don't want you to accelerate very much. So they're going to try and make sure you don't feel too uncomfortable. What is the net force on me? It's right in front of you. No. That is one of two forces acting on me. There's 600 newtons upwards, and there's 750 newtons downwards. The net force on me is 150 newtons downwards, which I could have gotten right at the very beginning of the problem. I didn't have to do any work to figure out the net force. The net force would have been 75 kilograms times 2 meters per second squared. The net force was 150 newtons the whole time. And we had that with the given information. Net force is the sum of all the forces acting on me. It's the result of the forces if they're unbalanced. All righty. This problem, we're trying to figure out the forces acting on the wagon. The wagon is being pulled to the right at 2 meters per second. I'd like you to tell me the normal force acting on the wagon and what the size of the resistive force must be acting on the wagon. As you guys said, this is a Newton's first law problem since the wagon is traveling at a constant speed. Go ahead and draw in the free body diagram that would describe the forces acting on the wagon. Should I draw in something for a fundamental force? Yes. I'll draw a downwards arrow. This arrow's the weight of the object and is 50 newtons long. I'm just going to write weight. Is there a string or a rope or a force pulling on the object? Yes. Yeah, I think I can probably state that this 10 Newton force is a tension acting on the object. But it's 10, so I'm going to draw it to be relatively small compared to the weight. Is the wagon in contact with any surface? Yes. So I will need to draw a force that is perpendicular to that surface. So I think an upwards arrow would be okay because that's the surface, the ground. So, but I'm going to draw this force intentionally less than the weight because it looks to me like the tension is also pulling up on the object, right? So both of those contribute to upward forces. Now, does that look balanced to you? No, I don't think it looks balanced to me either. There has to be something pulling to the right. Are there any forces that we know about in our list that might qualify here? Friction might qualify. It's rolling, so maybe not, but it makes the most sense that there be a force acting to the right that is approximately the same length as the force to the force to the left. That's approximately the same length as the force to the right. I'm going to label it friction, but it's some form of resistive force. I need a coordinate system that I can use to help solve this problem. So I can choose any coordinate system I want since the system isn't accelerating. But I give you a second priority, and that is to try and choose a coordinate system that's lined up with the most number of forces possible. So it makes sense to use a coordinate system like that. No, I think that would probably be a poor choice, don't you? Yes. So maybe a better one would be one that is like this, and therefore also like this. Now, since there's no acceleration, we can make whatever direction we want, positive and negative. So I'm going to go ahead and just do the standard positive x, positive y, negative x, negative y. Do I have any off-axis forces? Yes, I do. Because of that, we will have to take issue with these off-axis forces. I believe that this will be 20 degrees. So I think I will have to break this up into components, with a component being listed this direction and a component being listed this direction. Without doing a lot of explanation, I think this is going to be t sine 20 degrees, and this will be t cosine 20 degrees. Do I need to do more explanation than that? Okay, once you have broken a force up into components, the components take over for the force. Do not draw components on a free body diagram, but you can draw it on your working diagram. Everybody understand what I'm saying? Yes. You can't have components on a free body diagram, but this is our diagram that we're using to solve the problem. So I am going to ignore the blue arrow and only focus on the green arrow now. Everybody understand? They take over. So, net force in the x direction and net force in the y direction. I know I can't hold you. They both are 0. But I want to just quickly do this. T cosine 20 minus f equals 0. Right, those are the ones that are in the x direction. Now I see 3 things in the y direction. T sine 20 is upwards, normal force is upwards, and weight is downwards. Do you guys see that okay? Newton's laws generate these 2 relationships. You can then go in and put numbers in and try and figure them out. But Newton's laws kind of end there.